Come on in, everyone. If you have any questions, go ahead and ask. We've got a little bit of time. So no question. I don't see anything coming up on chat either. Hope you all had a good weekend. I'm sorry I had to miss class at the end of the week. Hopefully everybody got my message early so I didn't have to drive up here. I apologize if you didn't. Got about 1 minute left if you have any questions. I don't know if this is a root or not, but I'm not. It looks a little better when it's neater, a little scruffy. All right, looks like we got about 8 of you folks in here, and it looks like it's about time to start. When we were last working, we were in sort of chapter 7, sort of chapter 8. I sort of throw the two together and give you stuff from 7, stuff from 8 all at the same time. So believe it or not, even though we were in 7, we covered a little bit of 8. And even though now we're in 8, we're covering a little bit of 7. But one of the things I did at the last part of the notes last time was I gave you a way of using the work energy theorem. And the work energy theorem says that the work total, in other words, the work due to the net forces acting on the system, is equal to the change in kinetic energy. And I suggested, for instance, if you had a car wreck, you would actually see police officers sometimes measuring the skid marks, and the skid marks can be measured like that to actually get an idea of exactly how fast the car was going beforehand. So I thought I'd go ahead and start off by finishing that, and then we jump into some more examples from conservation of energy as opposed to the work energy theorem. So what we found was that work total, which you can literally define to be the integral of the summation of all the forces dotted with dl, turns out to be just equal to the change in kinetic energy. And of course, kinetic energy is defined to be 1/2 mv squared classically. And that's, I'm stressing that right now just to tell you that, because once we start to get within a percent or so of the speed of light, then we have to use an entirely different formula. But if we take this and we imagine a car potentially getting in a car accident, for instance, what we can do is we can realize that the network done is really, you've got a force pushing up. That's the normal force on the road, from the road onto the car. and you've got a gravitational force pushing down. And in fact, those two forces cancel each other out. So the net work in the vertical direction is zero. If you're treating the system as if it's both cars, then the force applied to one car from the other and vice versa, those are internal forces, so they don't count at all. You don't have to deal with those. All you have left really is just the external forces, which might be, for instance, the friction force between the car skidding their brakes and the road. And from that, you can get, as I'd say here, work total in that case might actually become negative times the friction force, and the friction force would be mu k, assuming it's a level street. The normal force would be mg, and then ultimately the skid marks might be a length L. That would be work total, and then the change in kinetic energy would be final minus initial. Remember, delta K always means K final minus K initial. That's what delta means in general. So in this case, we get K final, which is 1/2 m0 squared minus 1/2 mv initial squared. This obviously is just zero, and these minuses can become positive, in which case you get, noticing also, for instance, that the m cancels out with the m, and basically I get vi is equal to the square root of
Excuse me,
2.
Professor.
Yes.
We cannot see the screen.
Thank you. Thank you again. God, what is wrong with me? Yes, that would probably be helpful. And actually I have to do it this way. Jumped right in and didn't know what the poop I was doing. Thank you for letting me know. And I apologize for putting you in the difficult spot of having to do that. But anyways. Okay, so this should give you a little bit of time to catch up once you actually see it. So what I showed you was the work total is equal to, or defined to be, the summation of the forces integrated. And I don't even know why I wrote what I wrote there. I put a circle around the integral just out of habit. Let's do that. Let's just, whoa. Let me go back to using black. So the integral of the total force, that's what I mean by this symbol, is the sum of all the forces. So the sum of all the forces dot dl turns out to be the change in kinetic energy. I define the kinetic energy, and of course final minus initial is what the delta stands for. So in this case, I get negative mu k mgl. In case you're wondering where the negative came from, remember that the friction force might be, if the car is going that way, for instance, the friction force is going to be pointing this way. Therefore, the angle between the force and the displacement is 180, and the cosine of 180 equals -1. So that's why I get negative mu k times mgl. And again, we are assuming that the normal force is mg. So that means no incline. So that's how we use that. So now we've just got well, actually we got mu kg times L is equal to 1/2 vi squared. I can multiply both sides by 2. I get 2 mu sub k g times L. All that I take the square root of. And from that, if we take some typical numbers, I can say 2 times, let's say the coefficient of static friction is 0.10. Gravity, of course, is 9.80 meters per second every second. And let's say that a typical skid mark might be around 30 meters. Let's say 25 meters because it's a little closer to maybe 60 feet or something like that. So if we took that, what would actually be the initial velocity? Well, we'll do 2 times 0.1 times 9.8 times 25. That gives the square root of 49. And notice the units turn out to be meters squared per second squared. And now I take the square root of that, and I think everybody knows what the square root of 49 is. Should be 7. So we get equals 7.0 meters per second. Of course, you can convert that to miles per hour, but the main thing is that's a typical application of the work energy theorem. So by knowing that the skid mark was about 25 meters long, knowing that it went from some initial speed VI to 0, we were able to conclude, assuming the coefficient of kinetic friction, because it was skidding and therefore left a black mark, was 0.1, that gave us a speed of about 7 meters per second. And of course, like I said, we can't convert that to miles per hour. Let me do that real quick. 7 meters per second and miles per hour. The car was not going very fast. It was going about 15.6 miles per hour. Okay. But again, the main thing is I just wanted to show you how you could use that to have some sense of what the work energy theorem can do in terms of a car wreck. It's not completely uncommon, but it's not as often anymore. But occasionally people will call and ask for me or Dr. Wright or one of the other physicists to come and testify in a case about a wreck or something like that. And that would be basically the science we use. We use conservation of momentum, which comes up in the next chapter and stuff of that sort. Now, in addition to last time talking about the work energy theorem, we also discussed basically various types of potential energy and energy stored in a spring, or elastic energy is another thing to call. But just as a recap, let's go ahead and go over what we found. What we found was when F is equal to negative mg, let's say j hat, meaning we're assuming y points vertically upward, therefore gravity points vertically downward along the y-axis, and therefore the force of gravity, your weight, is negative mgy. For that case, what we found is the potential energy was equal to m times g times y, and the change in potential energy, of course, is equal to mg y2 minus y1. And your book makes a point to point out that you don't have to always use the same zero of potential energy, because ultimately what matters is the change in potential energy, not the exact potential energy. In other words, you can take any potential energy, mgy, and add an arbitrary constant to it, and it's not going to change anything. Okay, I'll show you an example with that in a second. I'm going to do this one and I'll write it in blue just to remind you that my memory might not be that good. So when we had a force that was equal to G M over r squared, and of course pointed radially inward, so I put the negative there, and then I did the r hat, which means that points from the origin to whatever point you're at. When the force is actually that, then we found that, and this is the part I'm trying to do with memory, so I'll say memory. So in other words, I'm telling you, hey, I'm writing this down off the top of my head, but you should look it up on your book to make sure. But basically what we found was U was equal to negative G, if I remember correctly again, M over R. And of course, delta U would be negative G M times 1 over R2 minus 1 over R1. So that's another fair game. But again, I just want you to remember that this is by memory, so don't trust it. I think I'm right, but I might be off by a mass or I think that's it. I'm pretty sure. Anyways, there was also another one. We could, for instance, find the potential energy associated with F is equal to negative kx. Remember, that's called, anybody remember what that law is called?
Law.
Yes, Hooke's law. And the negative, does anybody recall why the negative was there?
Because it goes back and forth.
Sort of. So if what I mean is if I stretch the X in the positive direction, the force that the spring applies to it will be in the negative direction. Whereas if I compress the spring in the negative X direction from the equilibrium point, then the force that will apply will be in the positive X direction. So that's really about which direction the force is, or another way of thinking of it is because it's a restorative force. So I could say it that way. Now, that's the force that the spring applies to the object. But the main thing was we were able to find that the potential energy was 1/2 kx squared, where x is the distance between equilibrium and where it's currently at. And of course, that also means delta U is equal to 1/2 k times x2 squared minus x1 squared. Again, just showing final minus initial. Those were some of the conclusions we reached. We also reached the conclusion that there was a quantity called kinetic energy, and the kinetic energy is given by 1/2 mv squared, so that delta K is equal to 1/2 m v2 squared minus v1 squared. So that's sort of the list of things we found very important. I mentioned to you that conservation of energy, which I'm going to write now. Conservation of energy, mechanical energy specifically, can be written like this, where you say delta U plus delta K is equal to 0. And this is the way a lot of textbook authors do it, and it works fine. It's just it doesn't allow you to put in sources of energy. Like if someone gives the kid a push on a sled, that would be work put in or some kind of energy put in. This doesn't allow that to be included. If somehow the kid on the sled compresses a spring, that can't necessarily be put in unless you treat it as another form of kinetic energy. So, another form of potential energy, which in that way it'd be fine. But in general, it's just, I haven't found it as convenient as I would like it to be. So I often use a slightly different form. And you can see where it comes from, because if you write delta U plus delta K, what you'll get is U final minus U initial plus K final minus K initial equals 0. But then you can sort of reshuffle that and you end up getting U initial plus K initial is equal to U final plus K final. And that works fine as well. These two are in fact exactly equivalent. But I use something sort of like that. So I'll say me. What I suggest you use is the following, and that's U initial plus kinetic energy initial plus work put into the system is equal to U final plus K final plus work out of the system. In other words, work put out by the system plus E loss. Now, I was telling my students today, if you wanted that more symmetric, you could actually add En or E gained. And that would be fine. At least then it would be a little bit more symmetric. So that's fine. But what I do is I basically use that work in to count for work in, meaning let's say we actually compressed a spring before we started studying it. And compressing a spring would be sort of like compressing a spring in a toy gun. You've given it some energy by compressing the spring. So that could be work in. But you could also say, well, I took the energy to push the ball into the spring-loaded gun system, and therefore I put energy in, or I gained energy, in which case you could call that E gained or E in if you wanted. Both of those are perfectly acceptable. What I want you to do is realize that it doesn't matter exactly what you call what, as long as you account for each type of energy being used. So, and you count for it once. So, well, actually, I don't want to go ahead and write all that sentence, but I'm just going to tell you, when you use an equation like this, the main thing is account for all types of energy. So if there's friction, you're going to account for some kind of work being done against friction. And if that friction will most likely be something you'd consider either E loss or work out, that would be perfectly fine. It's definitely taking away from the energy that you had initially. So you want it on the right-hand side. If, however, someone gave someone a push, that would be work put in, or you could consider it E in, or you could consider it E gained. But once you've accounted for it, account for it exactly once, and that's it. So anyways, that's this kind of stuff you can do. Now I'm going to turn into chapter 9 or chapter 8 and try to go over some of the main stuff your book talked about. What your book talked about specifically was starting off with the conservation of energy and talking about conservative forces. And specifically, it said, by definition, we call any force a conservative force if the work done by the force on an object moving from one point to another depends only on the initial and final position of the object and is independent of the particular path taken. That's what conservative forces mean. You can also think of them as none of the energy is being wasted in making heat by, fighting against friction and stuff like that. But the main definition is literally that the work done the work done by a force on an object moving from one point to another depends only on the initial 5 positions, not the path taken. So that's one big part of what a conservation law would entail. Conservation laws are made from conservation of energy, and energy is conserved if the forces are what we call conservative. And if they are conservative, we can make scalar potentials like U such that we get to work not with vectors, but with scalars. So that's kind of nice and helpful. You also can see some of the forces that are conservative are, for instance, gravitational, or Hooke's law, the elastic force, or the electric force. It turns out the magnetic force isn't really conservative, but you can find areas where it behaves a certain way, and then you could make up something called a vector potential, and that's just way far afield from what we're trying to study right now. But in the end of all this, there's this cool mathematical theorem that basically says, hey, if one of these are true, then they're all true. So if one of the statements below are true, then they are all true. So that's what we're going for here. And the first statement you might write as F is a conservative force. So F is a conservative force. 2, that tells us something mathematical, specifically something called del cross F, which is also called the curl of F, which is defined to be basically you could take this determinant of this matrix, which is I hat, J hat, and K hat for the first row of the matrix. Partial derivative with respect to X for the first column of the second row. Partial derivative with respect to Y for the second column of the second row, and partial with respect to Z for the third column of the third row of the second row. And then F sub X is here, F sub Y is here, and F sub Z is here. And this is identically 0. Now, what does identically 0 mean? Identically 0 means when you do all this crazy computation, it'll just come out to be 0 I hat plus 0 J hat plus 0 K hat. You don't have to choose a specific X or a specific Y or a specific Z or a specific 2 of those or a specific 3 of those or a specific time. You don't have to pick any of those with any specificity. It's automatically going to be 0. So just to not introduce something that I don't actually show you how to compute, even though I'm not going to ask you to compute that this semester, I will tell you that this turns out to be basically I hat partial of FZ with respect to Y minus the partial of FY with respect to Z plus J hat partial of FX with respect to Z minus the partial of FZ with respect to X plus K hat partial of FY with respect to X minus the partial of X with respect to Y. That's ultimately what that computation of that determinant is. So just to let you know what it is. So if F is conservative force, then the curl of the force is identically 0. There's another rule that says the integral from A to B of F, let's say F dot DL, in other words, we're calculating the work from one point A to another point B, is going to turn out to be, let's say, some V of B minus V of A, and is independent of path. So that means literally, as long as I go from point A to point B, I can go parallel to the x-axis, parallel to the y-axis, and then parallel to the z-axis, because that might be really easy to calculate, and that will be fine because the path doesn't matter. Or I might just go straight along the line y equals x. And again, if that's easy, that's a good thing to do, and I get a computation and I get a result, and it won't matter because it's independent of path. Or I could go and end up at B, and it doesn't matter still. So really, that's the beauty of that. And a ramification of this, which I think you could probably immediately see, is that the closed integral, that's something fancy we use in physics, is we put a circle around an integral. That's to remind us that we're talking about the integral over a closed path. And in this case, it's F dot DL. So we're basically taking the work done and going from, let's say, a point A, doing all sorts of crazy stuff, doesn't really matter, but ending up at point A. If that's the case, then the answer will automatically be 0. So that's another interesting tidbit. Remember, the rule is any one of these are true, then all of them are true. There's another rule as well. I'm going to show you some fancy mathematics here, mathematical symbols here. Upside down, backwards E means there exists. There exists a scalar function U such that, so that's a fancy little mathematical symbol as well. This one means such that. Okay. F, oops, wrong color. Such that F is equal to the negative gradient of U. In other words, we can work with the scalar function, this potential energy type function, which is not vectors, and therefore it's a lot easier. We can work completely with that and get answers and stuff. But if we ever want to get back to the vector state, all we have to do is take the negative of the gradient of U, and that will give us our force. So for example, let's look at this right now. When F is equal to negative mg j hat, we know that U is equal to mgy, right? So what is F given U is equal to mgy? Well, this is what it is. F is equal to the negative gradient of U. Now, what does the gradient mean? Well, the gradient means basically you write a I hat and then you take the partial derivative with respect to X, and you just leave a space because this is a operator. This is something that takes stuff on its right side and spits out new things. And if that thing on the right is a scalar, it's going to make it into a vector. And if that thing on the right is a vector, then you're either going to have to put a dot between this operator and the vector, or you're going to have to put a cross between this operator and the vector. And then there's something else that it'll become. So in this case, it's this partial with respect to Z. So that's the operator, and it's going to act on, so there's the negative sign. Don't forget that. Actually, I'm going to make this a little better. Let's say F is equal to the negative this times, now what our function was m times g times y, which you can see is just equal to negative mg. Now the only one that really survives is the j hat partial with respect to y of y. And of course, you can see that the partial derivative of y with respect to y is just 1. So we end up getting negative mj, or mg, j hat, which is exactly the force that we need to. Does that make sense to everyone? Okay. So that's another example. Now there's another thing down here, and I don't really want to number it or anything because it's got a lot of convoluted words and symbols and mathematical terminology and stuff that's not that helpful. I'll just tell you that it somewhat relates to the things for which a partial differential equation, or excuse me, for which a exact differential equation can be defined. So when you're in your differential equation class, you'll learn about exact differential equations. And I'll just tell you that these types of things allow you to create exact differential equations, the ones that look like some function of x and y times dx plus some function of x and y times dy is equal to 0. That's the typical scenario for a exact differential equation. So I'll say back to black. Also, F/U has some relevance to exact diff EQs. Okay. And I think that's sufficient for what I'm saying here. But that's kind of an interesting thing, and it's a nice thing that'll come in handy over and over again. As I said, the forces that are of this variety of conservative are the gravitational force and the electric force and the elastic force as a minimum. And of course, you can make other ones. So now that I've covered that part, does anybody have any questions on that? So your book goes through it. They spell this out without a lot of the details. They don't put it in that form like that. But when you take an electricity and magnetism course, for instance, they usually take the time to explain that. We've already talked about the gravitational potential energy and that sort of stuff. So what I like to do is let's consider an example. So let's say example. So let's imagine a roller coaster riding along, and then it humps up and then comes back down like this. Okay. I'm going to call this point right here A. I'm going to call this point right here B. I'm going to call this point right here C. And I am going to go further and say, oops, and say that the height from here to here is, let's say, 20.0 meters. And let's say the height from here to here is, whoa, is 10.0 meters. And let's say we have a little roller coaster car right here, and its mass is equal to 1,000 kilograms. So what I want to know is excuse me, if we use y equals 0 at HEIGHT A, what is delta U from from B to C? Or actually, let's ask another way. Let's say instead of delta U, let's say what is U of A equals question mark. No, not U of A. Let's do U of B equals question mark. So I'm asking for the potential energy at point B. And then I'm asking for the potential energy at point C. part B, I want to know what is delta U in going from B to C, which is UC minus UB. And then finally in part C, I want to know what is delta U B to C when the height of C is y equals 0. Okay. Everybody think they understand what's going on here? Anybody have any questions about that? So it's sort of like we're putting the coordinate origin either on that red line that's the same height as A, or we're putting it on this line right here. So this would be, for instance, for part C, this would be y equals 0. And for part A and B, this would be y equals 0. So let's start off with part A. So U is supposed to be mgy. So that means UB is equal to 1,000 kilograms times 9.80 meters per second times the height that the point B is above what we called y equals 0, and that's clearly 10.0 meters. So you can see that that answer will be positive 9.80 times 10 to the 4th joules. So that's one part of our answer for part A. Another part of our answer for part A is what is UC? Now UC is going to be 1,000 kilograms times 9.80 meters per second. Now this time the height is -20. Whoa. Is -20.0 meters. And for that, we get 1,000 times 9.8 times 20, which is really going to be about twice as big. So that's -1.96 times 10 to the 5th. And that's joules as well. So now we've done part A. Anybody have any questions on that? Now, part B and C are really the most important parts. So let's look at part B, where we're still using y equals 0 at the same height as A, but now they're asking you what is the change in potential energy when you go from point B to point C. Well, that's supposed to be the potential energy at C minus the potential energy at B, which should be equal to, of course, -1.96 times 10 to the 5th joules minus 9.80 times 10 to the 4th joules. So I'll say minus 9.8 e to the 4th. And this gives me -2.94 times 10 to the 5th joules. So that is the change in potential energy for part B using y equals 0 at height A. Now we're going to do the same thing for the height being 0 at height C. So now I'm going to say delta U B to C is equal to UC minus UB. Well, in this case, again, we're using U is equal to mgy, but in the case of UC, that's 1,000 kilograms times 9.80 meters per second every second times 0 meters, because that's how high C is with respect to C. Now I'm going to do minus 1,000 kilograms times 9.80 meters per second times, now our height is going to be a full 20 plus 10 or 30.0 meters. And when you do this, I get 1,000 times 9.8 times 30, and that gives me negative 2.94 times 10 to the 5th joules, which you can see is exactly equal to what we got before. And that's what we mean when I tell you that the change in potential energy is what matters. And now you see that the change in potential energy is the same for the two coordinate systems. Does that make sense to everyone? I got your message, Richard. Anybody have any questions on that? Okay, so that's a very typical type of problem you can solve. Again, the big point is we could call the y equals 0 at the lowest part of the roller coaster. We could call y equals 0 at part A, or we could realize that this whole roller coaster is a height of 1 meter above the ground, and we could call the ground height y equals 0. It doesn't matter, as long as you stick with it. Once you start using it in a given problem, you should be fine to go. So anybody have any questions on that? So I want to point out to you something that is going to come in handy. We sort of glossed it over a little bit, but when you get into the second semester of this course, it'll become even more relevant. And your book says many things about it. So for instance, in one case, they say, we can also define the change of potential energy associated with a particular conservative force in an equivalent way as the work done by an external different force to move the object without acceleration from one position to another. So that's something to keep in mind. If you put work into a system, so the change in potential energy is equal to the work put into the system. But another way of thinking about it, because sometimes you don't necessarily know what work you put into the system, you just know what work you did against the existing force. And in that case, you get delta U is equal to the negative of the work done by the conservative force. Bless you. So for instance, the work done by the conservative force could be work done by gravity. And that should make some sense, because if you imagine, for instance, I could take a force and use it to pick someone up, put them up on top of a fence post or a ladder or something like that. That amount of work that I did to do that is a certain number of joules. And now, because I moved that person from ground height to the top of the ladder or the top of the fence post or whatever, they have a potential energy that's equal to mgy, which turns out to be the bare minimum force that I could have applied to lift the person of mass m up, and then multiplied by the distance that I pushed the person, which is a distance y. So you see you get positive mgy. Now, if you actually computed what work was done by gravity in moving that person up, then gravity actually points down and therefore is a negative mg. And then you take a dot product of that with the dy, which would be in the upward direction, and you integrate it till it gets to the height. What you end up getting is m times g times y times the cosine of 180, which gives you a negative 1. So that's actually why you differ by a negative sign. So that's just something I think it's useful for you to realize. And your book talks about that in section 8-2-2 and other sections. So just keep that in mind. We're going to move on to the elastic potential energy, which I've already talked to you about. That's 1/2 kx squared. And then they go into a potential energy related to force. So I wanted to show you, for instance, an example like the example that they gave us. So let's look at another example. Suppose u of x, so we're treating this in one dimension here. That's why it just says u of x. So u is the potential energy function, is equal to negative ax over b squared plus x squared, where a and b are constants. What is the conservative force? So I've already hinted to you and actually showed you an example of how we can take a potential we did down here in the example in red. The force was actually negative mg j hat, and we were going to try to derive that from knowing that the potential energy is mgy, and we ended up getting negative mg j hat. So we're going to do the same thing again. What we know is F is equal to the negative gradient of u. In this case, this is going to become F is equal to the negative I hat partial with respect to x of negative ax over b squared plus x squared minus j hat partial with respect to y of negative ax over b squared plus x squared minus k hat. Notice I'm distributing the minus through here. That's why you're seeing multiple minuses. And this is the partial with respect to z of negative ax over b squared plus x squared. Now, the partial derivative is really just pretending like every variable other than the one you see in the bottom of the derivative is a constant. So in this case, there is no appearance of y. So I just took the derivative of a constant, and that's 0. And the same thing happened here. So all I'm really left with is this guy. So if I continue, I'm going to distribute the negative to the front and the a to the front. So I'll say positive a times, now there's only one variable present, so I might as well write d by dx of x times b squared plus x squared to the negative 1 power. Now, this is what I personally do in lieu of using the quotient rule for derivatives. I don't see any need and never had any need to do it. I just always treat it as if it's a multiplication of the first number times the second number, which is the bottom one, to the negative 1 power. So the product rule works just fine for me. I'll put the a out in front, and the derivative of x with respect to x is just equal to 1. So I'm going to just say 1, and now I've just got to write the other function unmolested like this. And now I've got to take plus, because the product rule says you take the derivative of one of the functions and you multiply it by the other function, and then you take the derivative of the other function and you multiply it by the first function. So I've taken the derivative of the first function. Now this term I've got to take and just write down the first function, but now I've got to multiply it by the derivative of the second function. Well, the second function is sort of like u to the -1 power. So that becomes -1 times u to the -2, which will be b squared plus x squared to the -2. And then the chain rule says I have to take the derivative of u with respect to x. So that's going to be 2x right here. So now I can say a is still out in front, and I'm going to get 1 over b squared plus x squared. And now I'm going to make use, actually, let me get that looking a little better. Now I'm going to take that negative sign and bring it out in front. And what I see is when I do that, now my numerator is 2x squared, and my denominator is b squared plus x squared to the 2 in the bottom. I'm going to get a common denominator. I'm also going to distribute that a, and I'm going to say a times b squared plus x squared minus 2ax squared. All of that's going to be under the common denominator, or over the common denominator of b squared plus x squared to the 2 power. When you combine these, you can see that I'm going to get ab squared plus ax squared minus 2ax squared. All that's going to be over b squared plus x squared to the 2 power, which I can now write as, notice the ax squared minus 2ax squared is negative x squared. So I can write this as just plain b squared minus x squared over b squared plus x squared raised to the 2 power. And all along the way, I just magically dropped the I hat. So I'm going to put it back in here right now and pretend like nothing bad ever happened. And that's actually the force. So we can finally say F for that particular potential is A times b squared minus x squared over b squared, whoa, Nelly, over b squared plus x squared to the 2 power, all of that in the I hat direction. Any questions on that one? So that's the way we calculate a gradient, for instance. Your book actually did it without the I hats at all. I mean, they mentioned the I hats in some previous stuff, but the main thing is, since it's one dimension, it really can only act in the plus or negative x direction. So that covers it. Anybody misunderstand anything? Anybody have any questions on how I got what I got? Anything like that? Okay. So yeah, in the next section, the book talks about the gradient function, and it shows the I hats, the J hats, and the K hats, and all that good stuff. But again, I've done that. And I just wanted to show you what that was. I've told you what I use for my conservation of energy. And your book gives you some sentences that are helpful. So conservation of mechanical energy. If only conservative forces do work, the total mechanical energy of a system neither increases nor decreases in any process. It stays a constant. It is conserved. So that's the conservation of mechanical energy. They can also say something along the lines, well, that's sufficient. And they also state a couple other ways, but normally you can think of it as just potential energy and kinetic energy. And then, of course, if there's a spring in there, then you have maybe gravitational potential energy in addition to spring potential energy, or something you could call as work done by a spring, all sorts of cool stuff. But the main thing is we need to be able to solve problems like that. So let's see if I remember one that I would like to solve. Oh yeah, here you go. So let's imagine a box falling from a height of 5.00 meters. Whoa, I don't know why I wrote cursive in there. How fast will it be falling I'll say A. How fast will it be falling when it is 2.50 meters above the ground? B, 1.00 meters above the ground. And C, just before it hits the ground. So that's our scenario. I'm going to draw it like this, say. So let's say we have a box. The initial height of it, of course, is h is equal to 5.00 meters. Something like that. What we want to know is when the height is A, V equals question mark. And then part B or part C. Well, I guess we can see it just close enough. I was going to write out all the details, but that's not really that necessary. So let's just go ahead and start. So for part A, what we're looking for is how fast it'll be going when it gets to half its height. So using my method, I would say U initial plus kinetic energy initial plus work in is equal to U final plus kinetic energy final plus work out plus E loss. Now, workout and E-loss are basically what I use for working against friction or compressing a spring or something like that. We're ignoring that kind of stuff. Well, we don't have any springs, but we're ignoring air resistance and friction. And the same thing with work in, we're assuming none of that happens. And in fact, since they said it was falling, in other words, imagine a box falling, that means the initial kinetic energy is 0 as well. So from this, we get basically, if I call the mass of the block M, they didn't give it to us, so there's no reason to necessarily assume it. I'm going to put it in there and hope that it disappears. But I'm going to say M times G times 5.00 meters is equal to, now at this point, I get M times G for the potential energy times 2.50 meters plus 1/2 MV 2.5 squared. And you can see that the M's all cancel out. That literally means, hey, I can divide both sides of the equation by M and they disappear. And in doing so, I can now say that V 2.5, I can say that V 2.5 is equal to the square root of 2 times 9.80, that's the G, meters per second per second. Now, on the left-hand side, I had the 5. So it's 5.00 meters. And then when I pull the 2.5 from the right-hand side, that's going to give me a negative 2.50 meters. And that's basically it. So now I can compute that. I'm going to take 2 times 9.8 times, now I'm going to do 5 minus 2.5. Oops, I didn't hit my decimal. And of course, 5 minus 2.5 is just 2.5. That gives me the square root of 49. Amazing. And notice that's meters squared per second squared again. And again, that gives me a velocity of the square root of that, which should be 7. And lo and behold, I get 7.00 meters per second. And I don't like that color. So that's the velocity when it reaches a height of 2.5 meters. Part B, they want to know what the velocity will be 1 meter above. So you can sort of look at this and realize it's still going to be the same thing. You're basically going to get V of 1.0 is equal to the square root of 2 times 9.80 meters per second times 5.00 meters minus 1.00 meters. Take the square root of all that. Now I'll say 2 times 9.8. 5 minus 1 is 4, so I'll say times 4. That's 78.4 meters squared per second squared. And now I'm going to take the square root of that. And that gives me 8.85 meters per second equals V of 1.0. And then the mystery question, which is the whole reason I asked about the 2.5, is do you think the velocity at 5 meters below, in other words, just before it hits the ground, is going to be twice as fast as it was at 2.5? Anyone? That's going to be 2 times 9.80 meters per second times 5.00. Oops. Yeah, 5.00 meters minus 0.00 meters. So in this case, I get 2 times 9.8 times 5, and that's 98. And then the square root of 98 is equal to 9.899. Actually, I should just go ahead and call it 9.90 meters per second equals V at 0.0. So no, it is definitely not double the speed at 2.5, but you shouldn't have expected that because remember the velocity in kinetic energy is velocity squared, whereas the height is linear. So you'd expect it to be more like a square root of 2. What's 7 times the square root of 2? 9.90. So that's exactly what that actually turned out to be. So by doubling the height it fell, I actually increased the speed not by a factor of 2, but by a factor of the square root of 2. Any questions on that? Okay, so your book does do a neat conceptual example. I'm just going to write down here. See conceptual example 8-5 because I've exceeded my time. Oh, no, I haven't yet. So scared me. 8-5, it's actually 640 that this is, not 620. So see conceptual 8-5. If you don't understand it, make sure you send me an email or ask me or something like that. I'll be glad to explain it. But basically, you have two people going down two water flumes. The two water flumes have the exact same height, and the two people leave at the exact same time, but their shapes are a little different. And it asks you some very specific questions that you can actually use conservation of energy concepts to get the answer to. So I definitely want you to try to, work it out before they give you the response and then read the response and make some sense of it. If you didn't get the right answer, then think about it a little bit more until you can find what you think might be the right answer, or at least that you can explain it as well as they did. So you can see there's a couple other little simple examples in this chapter on conservation of energy. Not really anything that's earth-shattering or difficult or anything like this. They do try to ultimately add non-conservative forces, dissipative forces, and stuff like that. And the way they do it's a lot different in my experience from the way I normally do it. But it does work. It's delta K plus delta U is equal to work done by non-conservative forces. The problem with that has been for me is being very careful about your negative signs and positive signs. So it's often not very helpful. But your book does give you a problem solving conservation of energy sort of section to help you figure that out. So let me show you another example. The roller coaster car in example 8.4 reaches a vertical height of only 25 meters on the second hill, where it slows to a momentary stop 8-16. I'm trying to see if this is the same roller coaster that we did before. It's a slightly different roller coaster. So let's see. Oh, missed a lot of cool problems here. Okay. Oh, what? Don't know what I did. That's not it. Sorry, I lost everything here. Hold on a second, folks. Oh, this one's pretty good. Let's do this example instead. So it says, let's do example. A dart has a mass of 0.212 kilograms and is used to compress a spring. A spring constant, we'll say, is equal to 500 newtons per meter, but it's used to compress the spring by 6.01 centimeters and then released. What I want to know is how fast will the dart travel? So this is another one where we can use what I like to use for the conservation of energy is U initial plus kinetic energy initial plus work in is equal to U final plus kinetic energy final plus work out plus E loss. In this case, we don't really have any friction losses, so I'll leave that away. I'll leave that 0. I'm not going to really take the spring and run it in. I mean, take the dart and run it into another spring or anything. So I'll take the work out away. I'm not really changing height. So to be honest with you, what happens here is if I'm shooting it horizontally, then the height initial and the height afterwards are equal, so they cancel out. But I do compress the spring. So what I'm going to get is 1/2 the mass of the dart times the velocity of the dart squared plus 1/2 K times the compression of the spring squared. Oh, the initial kinetic energy was 0. Sorry about that. Let's get rid of that. So remember, we're loading up the dart. So that means when we initially push the spring in, the velocity is 0. So the kinetic energy there will be 0. I was wondering how the signs were going to work out, but then I realized, it wasn't moving initially. So I'm going to have basically 1/2 kx squared for the work put in. And that's equal to 1/2 mv dart squared, like that. You can see that v dart is gonna be, notice I can cancel out this factor of 1/2 and this factor of 1/2, and I'm going to say v dart is equal to kx squared. Oops. It's equal to kx squared over m square root. So this is going to be equal to 500 newtons per meter for K. Did I say? Yeah, 0.0601 meters for X. That's got to be squared. And then I'm dividing it by the mass, which is 0.212 kilograms. That's the mass of the dart. And when I compute this, I'm going to take the square root of 500 times 0.0601. And then I'm going to divide that by 0.212, close parentheses. And that gives me 11.91 with one extra sig fig, of course, meters per second. Any questions on that one? Okay, so hopefully you're sort of seeing the way these things work out. I think the examples the book gives you are pretty good. You don't really have to work too hard to try to figure them out. Probably the only thing that's even remotely complicated is when it does the basically a swinging pendulum, because you got to remember that the length of the pendulum stays the same. Let's say it's a mass on a string and the string is L0 units long. Okay. Well, that L0 can hang straight down, and that would be the minimum of potential energy for the pendulum. But when it goes up an angle theta, then it's actually raised a little bit. And what you got to do is figure out a way to find out how much it raised. Well, you can take the L0, which is the length of the pendulum, and multiply it by the cosine of theta, and that'll give you basically this vertical component of L0. But that's not really what you need. What you need is basically the distance from the end of that component down to where it was. So what you got to do is do L0 minus L0 cosine theta, and that'll be how high it will be. So that's a little bit of a trick, but it's really not that hard. So I'll leave that to you guys. That's another excellent example. That's example 8, 9. So I'll say make sure you understand example 8-9. It's pretty straightforward, but it's the kind of thing that I would much rather you see. You look at it, read it, see if you can work it out, and then look at the approach, and then look at, or maybe even just look at the approach first. After you tried to figure it out yourself, maybe take the time to look at the approach and then try to solve it. If you still can't, then look at the solution and then close your book and try to solve it. It's really this interaction with the book and yourself and trying to solve stuff. That's really where the learning of physics comes from. So I'm trying to get you guys to use that as much as possible. So sometimes not doing an example, I think, is more helpful than doing an example. And that's what I'm hoping will happen here, because it's straightforward enough, but it's also symbolic enough where you can tax yourself a tad bit. Let me look and see if there's anything else, since we only got 1 minute left. Law of conservation of energy. The rest looks like just conceptual stuff. Dissipative forces. Yeah, we did that, or I talked about that. That's nothing there. Yes. They do get in section 8.7. So I'll say so earlier when I wrote down the potential energy and said, I think, and did all the caveat stuff. Okay. What I'm telling you is now you can see this in section 8-7. And just for me to check, it turns out that yes, they use what they ultimately decided was U is equal to negative G M over R, and R is greater than R of the planet. And this is the mass of the planet. So yeah, I was right in my memory, which is not always the case. And they actually get you to do a little bit of calculation, like a conservation of energy problem where the package is dropped from a high-speed rocket. Let me see if there's anything else that jumps out. Escape velocity. Yeah, you can immediately solve for escape velocity. That's pretty trivial. I've already done one like that. Power. actually, power is just equal to dw dt. So I'll mention that to you. Power is equal to dw over dt, which is often means power is equal to change in potential energy divided by time taken. So that's something you should consider, but that's really the only difference. Power, by the way, has units of work divided by units of time. So that would be joules per second, which are defined to be watts. That's about all you really need to know about the power part. There are some neat things that come from it. So for instance, P can equal F times V. That's kind of helpful from time to time, but that's pretty much it. Anybody have any questions before we split? There is a section on stable and unstable equilibrium. Definitely recommend you read that for conceptual understanding, but I think it's pretty straightforward. You guys are free to go. I'm waiting for the last person to leave in case anybody has any questions, but you're free to go. There should definitely be some 242 classes next semester. I'm pretty confident I have one of them. I'm actually might even have two of them. I usually have one online and one face-to-face, but I'm not really sure off the top of my head what my schedule is, but we certainly will have a 242 offered somewhere next semester. Probably at least two of them. Anybody else? I know Richard has some questions. Gabrielle got hers worked out. Logan came early. Did you have any questions, Logan? You get everything worked out? Is there a chapter 7 practice? Yes. If it's not showing right now, that means something is jacked up. So let me go over there real quick and make sure it's unjacked up. Chapter 7, chapter 7, chapter 7. Oh, yep, just left it out. Let's see if I got it here. Chapter 7. Nope, that's not it. Quiz. Okay, chapter 7 is now there. And let me make sure it works. Yes, it seems to work. It's got the right number of questions and the right number of points. So yes, chapter 7 is there. Thanks, Logan, for letting me know. I didn't even see it. I had it already made it, but just evidently forgot it. How about Alyssa? Do you have any questions, Alyssa?
Yes, I do. I was waiting for everyone to leave.
Gotcha. Would you like me to turn off the recording?
Yeah, you still get your now.
Gotcha. I'll